today's objective, students are going to use Newton's law of universal gravity to determine how the force of gravity changes between two objects, two spheres. So remember that for the universal law of gravity, basically anytime we have two objects that have mass, then they are attracted to each other by gravity. It doesn't matter what two objects they are, as long as they have mass and they're in the universe, they will be attracted to each other. The three variables that are important to this are, well, here's our example of an astronaut out in space floating above Jupiter, for example, a planet like Jupiter. The astronaut has mass, we'll call this mass 1 for object number 1. Jupiter has mass, we'll call this mass 2 for object number 2. And then they have a distance between their centers like this. So here's the three variables that are important to their gravitational attraction. Gravitational attraction is also called force of gravity, and oftentimes we refer to this as the weight, the astronaut's weight, for example. So the force of gravity equals, it's a fraction, and anything on top of the fraction, remember, is directly proportional to the force of gravity. That means when this gets bigger, it makes this bigger. Anything on the bottom of the fraction will be inversely proportional to the force of gravity, because when this gets bigger, it makes the fraction smaller, it makes force of gravity smaller. So here's our three variables: mass 1, or the astronaut, mass 2, or mass of the Jupiter, and the distance between them. So my question is, so looking at these three things, for example, the mass of Jupiter, how does the mass of Jupiter affect the force of gravity, the force of attraction between the planet Jupiter and the astronaut? Does more mass make more gravity, or less mass make more gravity? More mass. The more massive Jupiter is, the more it'll pull on the astronaut. So more mass makes more gravity. So does this mass 2, does it go on top or bottom of the fraction? So since more mass means more gravity, it's directly proportional, so it goes on top. Now what about the mass of the astronaut? Mass 1 of mass object 1. Does mass 1 go on top or the bottom of the fraction? Yes, it goes on top because more mass of the astronaut means more weight of the astronaut. More mass means more force of gravity. So both of the masses go on top, because anytime these increase, it's going to make the force of gravity increase. Anytime these decrease, it's going to make the force of gravity decrease. So they're directly proportional to force of gravity. What about distance now? The distance between the astronaut and Jupiter. How does distance relate to force of gravity? Does more distance between the two objects mean more gravity, or less distance means more gravity? Well, less distance means more gravity, because the closer these objects are together, the more the force of gravity. So distance is going to go on the bottom, because distance is inversely proportional. And we found out it's actually distance squared. Distance goes on the bottom of the fraction. The full equation actually looks like this. This is actually the universal law of gravitation, and we have m1, m2 on top and distance squared on the bottom, just like we said. But we also have to add big G. Big G is called the gravitational constant. We talked about this last time. This big G just turns the units, changes out, makes sure all the units work out. And the thing about big G is it's a constant. It never changes. It's the same for everything in the universe. Every single thing in the universe that's attracted together has the same amount of big G. Here is our equation. We're going to be using this over and over again today. But what we're going to be doing today, we're not going to use any actual numbers. We're going to be using arrow math the entire time. But this is a little more complicated than other examples of arrow math that we used all year, because it has 1, 2, 3, 4, 5 variables. Well, actually has 1, 2, 3, 4 variables and a constant. Big G is a constant. So remember, that's going to be easy, because this means big G is always going to have a horizontal arrow above it, because it's constant. It doesn't go up or down. It stays constant the whole time. So this one's easy. In all of our examples and on your quizzes and tests, this will be constant like this. Now masses can be up or down or constant. Distance can be up or down or constant. And then we're going to have to solve for the force of gravity. Here's we're going to do A, B, C, D, E comparisons. E comparisons today. All right, here's comparison A. Comparison A, it says, how does the gravitational force in the second example compare to the force in the first example? Well, here's our first example. We're going to say, let's say the force of gravity between these two spheres is 10 newtons. That's all we know. We know it's 10 newtons, and we're going to call this mass. Mass 1 is just going to be m, little m. And mass 2 is going to be the same. It's going to be the same. So we'll call this one m, and the distance between them is d. Now, to use arrow math, we always have to compare at least two different situations. So Here is our second example, all right? And here we have the first mass M1 is still M, the same, not changed. The distance between them is not changed, it's still D. And then look at this. Now the mass 2, you see what happens is twice what it was before. So this is the thing that's changed. So what we're going to be asking whenever we do these is comparing. And it's easiest to always go from the first to the second to keep your logic intact. First example we have here, our second example we have here, and the question is, what's going to happen to the force? All right, is the force going to be greater than 10 newtons for this second example? Is it going to be less than 10 newtons for this second example? Or is it going to be the same 10 newtons for the second example? Here's our example we're using. So here is our equation with the picture on the screen, so we can have them in one spot to compare. In order to do this, I'm going to be using a Google diagram. You're going to be using this Google diagram tomorrow for your simulation lab that you'll be doing next couple of days. So let's move over to the Google diagram. So here it is. I double clicked on it, opened it up, and here's our force, our universal law of gravity equation. And then, you have your arrows that you can click and drag and move around as you need to. Let's work on one of these at a time. My first question is, what are we going to put above big G? Big G going to be constant? Is it increasing or is it decreasing? What are we going to put above big G? Well, big G is always going to be easy, right? It's going to be constant because it's a universal law of gravity constant, big G. So that one's always constant. Now, for the other three on this side, we have to look at our pictures and compare them. So looking at our pictures, when we go from here to there, let's look over here at, let's do mass 2 first. Mass 2, over here. Over at mass 2, I'm looking at this going from here to there. You notice there's a difference here. It began, in the beginning it was mass, it was just M, but now it's 2M. So looking at this in our example, what's happening to mass 2? All right, is the mass increasing, decreasing, or staying constant? Mass 2, are we going to put increasing, decreasing, or staying constant? What's going to go above mass 2? Well, it's going to be increasing because it was M and now it's 2M. You can even see it got bigger on my picture. So the mass increased, it got larger. Now, let's talk about mass 1. What is mass 1 doing? Go from here to here. What's mass 1 doing? Is it increasing, decreasing, or staying constant? Mass 1. Mass 1 is constant. We can see it was M and it's still M. It didn't change size or mass, so it's the same amount of mass. Now let's move over to distance. What's our distance doing? Increasing, decreasing, or staying constant? It is constant. Okay, the distance is constant. So now we have to solve. If we're looking at this, looking at our fraction, the bottom's constant, so we can basically ignore that. Look at just the top. These two are constant, so all we have is this going up. So if the mass is going up, the only thing we have happening is the mass is increasing on this side. What does that make happen to the entire fraction when the mass increases? So what has to happen to the force of gravity? The force of gravity has to increase, okay? Because as this increases, the whole fraction gets bigger because this gets bigger. And since this side gets bigger, both sides are equal. So the left side also has to get bigger. So force of gravity has to increase. All right. So what does this tell us? Let's go back to our picture. And now we have this. All right. Here's our equation. We figured out the force of gravity has to increase. So what's going to happen to this force here? Our explanation might look something like this. The force in the second example will be greater than 10 newtons because mass is directly proportional to force of gravity. Doubling the mass, too, would increase the force of gravity, right? Because since mass is directly proportional, making this bigger also makes this bigger. Remember, directly proportional means they move in the same direction. More mass means more force of gravity. Now we're going to try another comparison. Here's comparison B. How's the force in the second example compared to the force in the first example? So here's our pictures. Okay, you can notice here's our masses and our distance. And now going to our second picture, now we have half of a mass over here in the distance and then the mass there. I already put the arrows in here and they're hidden underneath these pictures. So we'll just go through and ask you, all right, look at our picture now. The first one we want to do is big G. What goes above big G? Is big G constant? Is it increasing or decreasing in our example? It is constant, right? It's constant because it's always constant. Now let's go to mass 1. What's happening to mass 1? Looking here, is mass 1 increasing, decreasing, or staying constant? What goes above mass 1? It is decreasing because it went from mass to half of the mass. It got smaller, less mass, so it's going down. What about mass 2? What's happening with mass 2 going from here to here? Is mass 2 increasing, decreasing, or staying constant? It is constant. It's staying m both times. What about distance? Right here. Is distance increasing, decreasing, or staying constant? It's constant. It's staying the same distance apart in both cases. Now we look at this and solve. Notice the distance is staying constant at the bottom, so we can ignore that. On top, everything's constant except for mass. Well, mass is going down, so since this goes down, what happens to the whole fraction? Since this side goes down and they're equal, so this makes the force of gravity do this also. So what it goes above the force of gravity? Up, down, or constant? It goes down because since the right side is going down, the left side has to go down because they're equal. So force of gravity decreases. So it's going to decrease from 10 to something smaller. So here's our explanation. If we wrote it out, the force in the second example will be lower than 10 newtons because mass is directly proportional to the force of gravity. Cutting the mass 1 in half would decrease the force of gravity. Since mass 1 is going down and it's directly proportional, force of gravity goes down, so less than 10. All right, let's try comparison C. Here we have our first example and then our second example. Okay, let's go through these now. What goes above big G? Constant, we know that already. What goes above M1? It is also constant. It's M here and it's still M, so it's constant. What about above M2, mass 2? It is also constant because it's m here and still m there. It's constant. Now what about above distance d? It is increasing because we went from d to 2d. You can see that they got farther apart. So distance went up this time. All right, now we have to solve for force of gravity. This one's trickier because distance is on the bottom and it's getting bigger. But since distance is on the bottom, it's going to have a different effect on the fraction than the things on top, right? We're dividing by a bigger number. So when you divide by a huge number, a big number, what happens to the fraction? And they're both sides are equal. So whatever happens to this side also has to happen to this side. So what goes above the force of gravity now? Up, down, or constant? All right, it goes down because more distance, the bigger you make the bottom, you're dividing by a bigger number. That makes the whole fraction smaller, so equal. Since this side's getting smaller, because you're dividing by a big number, when you divide by a big number, you make it smaller. Since this side's getting smaller, the force of gravity also gets smaller. So the force of gravity has to be less than that, all right? So here's my explanation. The force in the second example will be lower than 10 newtons. Oops, I wrote 10 newtons, but it's not really 10 newtons, it's 5. The force in the second example will be lower than 5 newtons because distance is inversely proportional to gravity. Doubling the distance will reduce the force, right? More distance means less force of gravity. And we know that the farther apart you move them, the less gravitational fraction will be. Let's try this example. Comparison D. What goes above M1? What goes above M1? That one is increasing. It went from m to 2m, so it is increasing. What goes above G? It's constant. Yeah, it's always constant. It's a universal law of gravity constant. Now what goes above M2? M2. It's increasing. It goes from m to 2m, so it's getting bigger. What goes above the distance? Distance is constant. It stays the same distance apart. Now you have to solve for this. Increasing and increasing on top, the bottom stays constant. So what happens to the overall fraction on the right? Whatever happens on the right has to happen on the left. So what goes above the force? Increases. Since the right side is getting bigger, the left side has to get bigger, so force of gravity has to increase. So looking at our example, the force in the second example will be greater than 10 newtons because mass is directly proportional, right? More mass means, and both masses are going up actually, more mass means increasing the force of gravity. So more gravity pulling them together. Comparison E, last example. Let's look at this one. So above the G, we already know it's constant. All right, above M1, what goes above M1? It's constant, M, and then M2 is also constant. Both of these have the same masses as before. Distance, so what goes above distance? What's happening when we go from this picture to that picture? What's happening to the distance? Is it increasing, decreasing, or staying constant? It's decreasing, right? It went from d to half the distance. You can see it got closer together. Ooh, and distance is on the bottom. So what's going to happen to the force of gravity? On the bottom, we're making a small number. So we're dividing by a tiny number. So anything on the bottom, less distance means a fraction does what? And it has to do the same thing on the other side. What goes above the force of gravity? Now we're closer together. Increases, right? Because this is since it's on the bottom, less distance means more force of gravity. Closer together means more gravitational attraction. So our statement looks like this. The force in the second example will be higher than 10 newtons. I did that again. It's 5 newtons. It'll be higher than 5 newtons because distance is inversely proportional to force of gravity. Reducing the distance increases the force of gravity. Less distance means more force. It's on the bottom. It's inversely proportional. So there's our E examples.